So by the name, I'm Mr. Bakari Musa, maths chemistry teacher. But today our lesson is going to be on organic chemistry 1, which is Form 3 work. So on the previous lesson, we started with the introduction and we looked up to alkanes, and we were supposed to start on rules when it comes to naming of alkanes and isomers, where we said that alkanes have one type of isomerism, which is the branching isomerism. Branching isomerism is where the substituent group alkyls are being formed. And during naming of the isomers, there are some of the rules that needs to be observed when naming isomers. So we check on rules on naming. So the first rule that we use is when identifying the parent name of the alkanes. When identifying the parent name of the alkanes, we identify the longest chain that contains the highest number of carbon atoms that will give us the parent name. So the first one is the parent name given by identifying the chain with the highest number of carbon atoms. 2, the second rule that needs to be observed when naming the isomers is to identify the position of the substituent group, which is the alkyl. Identifying the position of the substituent group. Identifying the position of the substituent group. When we talk about identifying the position of the substituent group, we are supposed to give it the lowest number possible on the structure. For example, if we have this one here, we put a methyl, that is hydrogen, 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 hydrogen. This is hydrogen, 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 hydrogen. From this one here, first we identify the parent name. The parent name will be given with the chain containing the highest number of carbon atoms. According to this, the highest number of carbon atoms is the straight chain with 4 carbon atoms. 1, 2, 3, 4. And we have the group, which is a methyl here. So the substituent group we have here is known as the methyl. Now when it comes to naming now, if we start naming the carbon atoms from this end, which will be position 1, position 2, position 3, position 4. And if we start from, it will be position 1, position 2, position 3, and position 4. Therefore, we find that the substituent group, which is a methyl, is nearer to this carbon atom if we start naming from this end. Therefore, we are going to name it as 2-methyl butane. 2-methyl butane. So butane is the parent name with the longest number of carbon atoms, which is 1, 2, 3, 4. And we have the substituent group, which is a methyl, found on carbon number 2. Then rule number 3, if we have the substituent group more than 1, we use the word di to represent 2, tri to represent 3, tetra to represent 4, and penta to represent 5. So we use the following words. The following words are used when the substituent group is R more than 1. So we use the word di, tri, tetra, etc. For example, we might have 1, 2, 3, 4. We have 5. So we put that one there. We have CH3, CH3, hydrogen, 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 hydrogen. So we have the two substituent group, a methyl and a methyl. Therefore, if we start naming the carbon atoms from this end, this is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5. Therefore, the methyl is found on carbon number 2 and carbon number 3. If we start from this end, this is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5. Therefore, our substituent group is going to be found on carbon number 3 and carbon number 4. Therefore, we are going to find that the substituent group is going to be nearer when we start naming these carbon atoms from this end. Therefore, it will be found on carbon number 2 and carbon number 3. Since we have 2-methyl, we name it as 2,3-dimethyl. The parent name has got 5 carbon atoms, 1, 2, 3, 4, 5. Now that one is named as pentane. Therefore, we name this one as 2,3-dimethyl pentane. 2,3-dimethyl pentane. 2,3-dimethyl pentane. So this gives us the third rule when it comes to naming of the isomers. Then another rule is, number 4, when we have halogens in the structure and the substituent group, we consider halogens first before the substituent group. So we say that halogens are considered first before the alkyl group, the alkyl group. So we give consideration to the halogens. Example, we have 1, 2, 3, 4. We have a methyl there, and we have chlorine. So we have this one as hydrogens. Those are hydrogens. Those are hydrogens. Now, how do we name this? So if we start naming from this end, this is carbon number 1, carbon number 2, carbon number 3, and carbon number 4. This is number 1, number 2, number 3, and number 4. If we start naming from this end, we find that the methyl is found on carbon number 2, while chlorine is found on carbon number 3. But if we start from this side, the chlorine will be on carbon number 2, and the methyl will be found on carbon number 3. Therefore, we start naming from this end, since we have said that when we have a halogen and the substituent group, that's in the alkyl group, we give consideration to the halogens first. Therefore, it is named as 2-chloro, 3-methyl, the longest chain with 4 carbon atoms, butane. 2-chloro, 3-methyl, butane. 2-chloro, 3-methyl, butane. So those are some of the rules when it comes to naming of isomers of alkanes. Naming of the isomers of alkanes. Now the next step is to check on how we can be able to prepare alkanes in the laboratory. How do we prepare alkanes? Preparation of alkanes. So we check on lab preparation of alkanes. Lab preparation of alkanes. So preparation of methane When it comes to preparation of alkanes, we use soda lime with the salts alkanoids. Alkanoids are salts derived from the organic acids. For example, if you need ethanoate is derived when you react a metal or a base with the organic acid ethanoic acid. If we react ethanoic acid with sodium hydroxide, we get sodium ethanoate plus water. If you need propanoate, we use sodium hydroxide plus propanoic acid, giving us sodium propanoate. So we have said that when it comes to preparation of alkanes, we use the alkanoids, which are salts derived from organic acids, with the soda lime. So we say are formed by reacting metal alkanoids or sodium alkanoids, which are salts, and soda lime. Soda lime is a mixture of sodium hydroxide and calcium hydroxide. Mixture of sodium hydroxide and calcium hydroxide. So that is the soda lime. Now the alkanoate used in the preparation of alkane needs to have one carbon atom more than the alkane to be prepared. For example, if I need to prepare methane, I will use sodium ethanoate from ethanoic acid. If I need to prepare ethane, I will use sodium propanoate. And if I need to prepare propane, I use butanoate. So for example here, we want to prepare methane. So methane is going to be prepared. We use here soda lime. That one here is aqueous plus ethanoate, sodium ethanoate, which is CH3COONA, aqueous. So what are we going to get? When we carry out this reaction, we are going to obtain sodium carbonate. This one here is aqueous plus CH4 gas. So this one is sodium ethanoate. This is the soda lime giving us methane gas. So the mixtures are put in a round bottom flask and heated together. Then the gas here is going to be collected by over water method, since it is insoluble in water, slightly soluble in water. This gas here is non-polar. Organic compounds like methane, the hydrocarbons are non-polar, therefore they do not dissolve in water, and collected by over water method. Let's check if we want to prepare ethane. This is preparation of methane. Now if you need to prepare ethane, what do we use? We are going to use soda lime, which is NaOH, aqueous, sodium hydroxide, taking part in that reaction. We use CH3CH2COONA, aqueous. This one is sodium propanoate. This is sodium propanoate. We are reacting it with sodium hydroxide, giving us sodium carbonate. This one here is aqueous plus C2H6 gas. We have already prepared ethane gas. So that gives us the lab preparation of alkanes. But remember, when in the previous lesson, when we were looking at the sources of alkanes, one of the sources of alkanes we talked about natural gas, we have biogas, and we had crude oil. And we said that crude oil forms the main source of alkanes. And the components of crude oil are separated by fractional distillation. This is because these components or those substances that are obtained from the crude oil, they have got different but close boiling points, and at the same time they also have different densities. That is the natural way on how to obtain alkanes, but this is lab preparation of alkanes in small scale. If you want to prepare alkanes in small scale in the laboratory. Now what I want us to check is the physical properties of alkanes. Example, we have methane, physical properties of alkanes. Physical properties of alkanes. One, for example, we talk about the methane. We are concentrating on methane. Methane. We talk about the color. Methane is a colorless gas. Methane is a colorless gas. So the first one is colorless. A colorless gas. Two, we talk about solubility. So when it comes to solubility, here we are going to check the general in alkanes. So if you look at the solubility of alkanes, alkanes are insoluble in polar solvent. Alkanes, so we say, are insoluble in polar solvent. When we talk of a polar solvent is that solvent that possesses both charges. It has both positive and a negative charge. And example of a polar solvent is water molecule. So if you look at water molecule, we have here oxygen, we have this one as hydrogen, this one is partially charged, this one is partially what? Negatively charged. This is a molecule of water. So we say water is a polar solvent that it possesses the negative charge. So organic solvents are insoluble in polar solvent, but soluble in organic, into bracket non-polar, soluble in non-polar solvents. Examples of the non-polar solvents, we have chloromethane, we have methyl benzene. Those are some of the examples of the non-polar solvents. So they are soluble in the non-polar solvents, which are the organic solvents. Now, how chemical pairs in alkanes? You will find that the solubility of alkanes will be decreasing down the group as the molecular mass increases. So we say solubility decreases with increase in molecular mass. So as the molecular mass increases, which means that the density also increases. Therefore, this is going to result in decrease in solubility in alkanes. So for example, if I have CH4 and C6H14, this one is hexane, this one is methane. So you find that methane is going to be more soluble compared to hexane. Methane becomes more soluble than hexane. Then the next one is melting and boiling points. Third one is melting and boiling points. Boiling points. What determines the melting and boiling point of a substance is the force of attraction existing either between the molecules or between the atoms or between the ions. So if we have the strong force of attraction existing between these particles, therefore we are expecting that substance to have high melting and boiling point. But if it has weak forces of attraction, therefore the substance is going to have low melting and boiling points. Now when we check in terms of structure and bonding, we find that these are molecular substances, and molecular substances have weak intermolecular forces of attraction. So since they have weak intermolecular forces of attraction, this also indicates that they are going to have low melting and boiling points. So they have low melting and boiling points. But though they have low melting and boiling points, the intermolecular forces of attraction is also being determined by the molecular mass. As the molecular mass increases in alkanes, the strength of the intermolecular forces of attraction also increases. Therefore, this results into increase in melting and boiling points in alkanes as the molecular mass will be increasing. So we say that being molecular substances, they have low melting point and boiling points. Low melting and boiling points. But the their melting point and boiling point increases as molecular mass increases. As molecular mass increases. So as the molecular mass increases, the strength of the intermolecular forces of attraction also increases. So we say this results into increase in strength of intermolecular forces of attraction. Forces of attraction. Intermolecular forces of attraction. Just like if we have here methane and we have here hexane, you find that hexane has high melting and boiling point than methane. This is because hexane has bigger molecular mass with strong intermolecular forces of attraction than hexane. But the type of intermolecular forces of attraction existing between the molecules are the same, which is weak van der Waals forces. They all have the same intermolecular forces of attraction, which is weak van der Waals forces. But now in hexane, it will have stronger forces of attraction due to its bigger molecular mass, making it to have high melting and boiling points compared to methane. Then the last physical property that is area of the alkane is the density. The density of a substance is determined by its molecular mass. So we have seen that as the number of carbon atoms increases in alkanes, their molecular mass also increases. Therefore, we are also going to find that the melting and boiling point, the density is also going to increase as the number of carbon atoms increases. So we say density increases with increase in molecular mass. With increase in molecular mass. So as the molecular mass increases, the density in alkanes also increases. Now the second part, after the physical properties, now we check on chemical properties. When we chemical properties is how alkanes react with other substances. That's what we mean by the chemical properties. How does it react with other substances? How does it react with other chemicals or other elements? Let's talk about as the chemical properties. So we check on chemical properties in alkanes. So, chemical properties in alkanes. The first chemical property we are going to check is combustion or burning in air. The first one is burning in air or combustion. Combustion. At the beginning of the topic, on the previous lesson, we saw that alkanes are saturated. And what does saturated means? We said that alkanes are said to be saturated due to the presence of single bond between carbon-carbon atoms. They have single bond between carbon-carbon atoms, making alkanes to be saturated. So, how do saturated organic compounds burn in air? Alkanes being saturated, they burn in air with a blue and less sooty flame. So we say alkanes burns in air with a blue and less sooty flame because they are saturated. Alkanes are said to be saturated. And what is the product formed when alkanes are burning in air? The product formed when alkanes burns in air depends in two conditions. The first condition is when we have in excess supply of oxygen, and the second condition in limited supply of oxygen. In excess supply of oxygen, we are going to get water and carbon dioxide. In limited supply of oxygen, we are going to get water and carbon dioxide. So when we get water and carbon dioxide, we say that is complete combustion of alkanes. But when we get carbon dioxide and water, that is incomplete combustion of alkane. So we have, for example, if we burn here methane gas plus oxygen gas, this results into formation of carbon dioxide plus water, liquid. Anytime you write a chemical equation, that chemical equation needs to be balanced. Therefore, we put here 2 and here we put 2. So that gives us carbon dioxide. Now here we put excess. Therefore this is complete combustion of alkane. If it is incomplete combustion of alkane, meaning that we are having limited supply of oxygen, we said instead of getting carbon dioxide, now we get carbon dioxide. Therefore the equation of the reaction is going to be CH4 gas plus oxygen gas, giving us CO gas plus H2O, liquid. So we balance the equation. We have 1 carbon, this is 1 carbon. 4, we put here 2, therefore hydrogen. Oxygen here is 2, here we have 3 oxygen. We can put here 3 over 2. That equation is balanced. Or we multiply everywhere by 2. This one by 2, now we get 2 CH4 gas plus 3 oxygen gas, giving us 2 CO gas plus 4 H2O liquid. So that's the product that's going to be formed. Here we have limited. This is limited. So we say incomplete combustion. Incomplete combustion. So incomplete combustion of alkanes results in the formation of carbon dioxide and water. This gives us the reason why when you are using a kerosene stove in a room which is not well ventilated, this may result to death, since there is going to be insufficient supply of oxygen, and we know that the paraffin or the kerosene, when there is limited supply of oxygen, there is going to be emission of carbon dioxide, and carbon dioxide is known as a silent killer. When you inhale this gas, it is going to combine with the hemoglobin contained in the red blood cell to form a stable compound known as carboxyhemoglobin. Carboxyhemoglobin cannot dissociate. Therefore, this lowers the transportation of oxygen, causing suffocation and eventually death. So when using a kerosene stove, you must ensure that the room is well ventilated for excess or enough supply of oxygen for us to have complete combustion of alkanes, because paraffin or the kerosene is an alkane, and when these compounds are burning, they need to have complete combustion for us to obtain carbon dioxide, which is not harmful to the environment or even to the human beings. So this gives us the first chemical property of alkane. The second chemical property is substitution reaction. Substitution reaction. Alkanes being saturated, they undergo substitution reaction. They undergo substitution reaction with halogens. What do we mean by substitution? To substitute. Substitute means you are removing something in place of another one. So alkanes being saturated, the hydrogen are going to be substituted with halogens. So this reaction, for it to occur, there is a condition needed for it to take place. And the condition needed for substitution reaction is sunlight or the ultraviolet rays. Why do we need sunlight, or why do we need the ultraviolet rays? The UV light is being needed to break the molecules into atoms for the reaction to take place. So we say alkanes being saturated, they undergo substitution reaction with halogens. They undergo substitution reaction with the halogens. The condition needed for the reaction, this reaction is sunlight or ultraviolet rays. So we said light energy is needed to break the molecules into atoms for the reaction to take place. So light energy is needed to break the molecules into atoms for the reaction to take place. So that's the condition needed for that reaction to take place. Now, how does the reaction takes place? One of the products being formed is the hydrogen halide. After the hydrogen atom being substituted with the halogen. For example, we look at methane. If you have methane, which is C hydrogen, and I'm using the open structural formula when carrying out that chemical equation plus the chlorine molecule. So one of the hydrogen is going to be substituted. Helium is chloride. Therefore, we are going to have here, we must have sunlight as the condition for the reaction to take place. We have that one there, hydrogen, and chlorine. So we are substituting the hydrogen here with a chlorine atom. And the remaining chlorine reacts with the hydrogen, giving us hydrogen chloride gas. So two products are going to be formed. We have the hydrogen chloride, and this one now is named as chloromethane. 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 This reaction does not stop at that place. As long as there is less halogens, like hydrogens are going to be is to obtain tetrachloromethane. For example, we now take the product that has been formed here, we add more chlorine, so we have C, this is hydrogen, 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 chlorine, we add another chlorine, this gives us C, chlorine, chlorine, hydrogen, hydrogen, plus the hydrogen chloride. Now we name this one as dichloromethane. We name it as dichloromethane plus the hydrogen chloride. Then here we have UV light as the condition. Then dichloromethane is also, we still add more. So we have C, that is chlorine, chlorine, hydrogen, hydrogen, plus chlorine molecule again, giving us C. This one is hydrogen, chlorine, chlorine, chlorine. There we have UV light, plus the hydrogen chloride gas. Now, this one we have three of them giving us trichloromethane. Trichloromethane. And if we continue, we have C, that is hydrogen, chlorine, 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 plus more of chlorine gas, giving us C. So here we have chlorine, 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 plus the hydrogen chloride. This is now known as tetrachloromethane. Tetrachloromethane plus the hydrogen chloride. You can see that all the hydrogen atoms have been substituted by chlorine atoms, now named as tetrachloromethane. Sometimes in a question, you can be given the mole ratio at which the reactions are taking place, whereby you have been told that write an equation of the reaction when methane is reacting with 2 moles of chlorine gas, 2 moles of chlorine. So here you are going to use the mole ratio of equation, mole ratios, for you to write the chemical equation that is taking place. So we are carrying out equation of the reaction, which is 2 here because in methane and 2 moles of chlorine. So how does that equation going to be? We have methane, which is CH4 gas plus 2 moles of chlorine gas. So we have said that one of the products that must be formed is the hydrogen chloride. So we have here HCl. And we have said that, again, this reaction occurs in a is 35. Therefore, we are going to have plus CH2Cl2 gas. So this is named as dichloromethane. Dichloromethane. To balance off the equation, we put here 2. So we have dichloromethane plus the 2 moles of the hydrogen chloride. Meaning, now I'm writing the chemical equation using the mole ratios of equations. And this reaction, we have said the condition needed is the UV light. And the function of the UV light or the light energy is used in the breaking of the molecules into atoms for that reaction to occur. So those are the 2 chemical properties that alkanes undergo. So we have said the first one is combustion, which is burning in air, whereby they burn with blue flame, resulting in the formation of water and carbon 4 oxide. That is complete combustion when we have excess supply of oxygen. If it is incomplete combustion, meaning that we are having limited supply of oxygen, we are going to get carbon 2 oxide and water. And the flame is a blue flame since they are saturated. And saturation is due to the presence of single bond between carbon-carbon atom. And the second chemical property of alkanes is the substitution reaction, whereby we have said to substitute means to replace. You are replacing something. So I'm removing one of the substance to put another one in place. Therefore, that one is known as substitution reaction. And alkanes undergo substitution reaction since they are saturated. And that reaction giving occurs when they are reacting with halogens. And the condition needed for a substitution reaction is the UV light, or the light, the sunlight, which is required in the breaking of the molecules into atoms. And the last part of alkanes is uses of alkanes. What are some of the uses of alkanes? Uses of alkanes. So we are to check on uses of alkanes. Uses of alkanes. Uses of alkanes. One use of alkane is source of hydrogen. That is during cracking of long-chained alkanes. Source of hydrogen. So we talk of source of hydrogen during cracking of long-chained alkanes. What is the importance of the hydrogen? Hydrogen is used in Haber process in manufacture of ammonia. We also use the same hydrogen in manufacture of hydrochloric acid. We also use hydrogen in hydrogenation, which is converting of oils into fats. When we say that oils are unsaturated while fats are saturated. So we say here source of hydrogen, that is during cracking of alkanes. So hydrogen is used in Haber process and in manufacture of hydrochloric acid. Hydrochloric acid, though hydrogen also still has some other uses. Then we have the second use. We have gaseous alkanes, that is like methane, ethane, propane. Those ones are used as domestic fuels. We have gaseous alkanes being used as domestic fuels. We have gaseous alkanes being used as domestic fuels. Even there back at home, you can see the cylinders. We have the gas cylinders. So today maybe you can go check when the gas cylinder is burning, try to turn the room to be dark and light that gas cooker and try to check the color of the flame that it will be producing. Is it really producing the blue flame that we are talking about? Because we said that when alkanes are burning, they burn with the blue and less sooty flame. So you can try check the type of the flame that gas cooker will be producing when you turn it on during combustion. And the third one, we have alkanes which are also being used in making of the carbon black. Carbon black is a component of the printer's ink or even the shoe polish. We have the kiwi. That for that shoe polish to be black or to be the way it is, the way it looks like, there is a substance known as the carbon black, which is obtained from alkanes being added there. So we say making of carbon black, which is a component of printer's ink and shoe polish. And we have the fourth one, used in manufacture of alkanols and alkanals. Manufacture of alkanols and alkanals. So that is going to give us some of the uses of alkanes, whereby in this one, when we are carrying out cracking of alkanes, one of the products being formed is the short-chained alkanes. We get an alkene, and alkenes, which is going to be our next lesson, we carry out hydrolysis of alkenes for us to be able to obtain alkanols. Alkanals are also other substances which are also going to be formed during the process when we use alkanes. So this gives us some of the uses of alkanes. But remember, we have wide range of uses of alkanes. Wide range of uses of alkanes, and some of the alkanes that we talked about obtained from the crude oil, you need to remember, we talked about the bitumen, which is used in road tarmacking and also in sealing of the rooftops where there is some leakages. We also talked about the naphtha, which is used as a solvent. Maybe in manufacture of drugs we have the naphtha. And we also talked about the lubricating oil, which is used in lubricating the movable parts of the machines. This one is to reduce the friction. So this gives us some of the uses of alkanes, and that brings us to the end of the subtopic under alkanes. And now the next topic we are going to start is on alkenes. That's under the hydrocarbons, organic 2. That topic will be on alkenes.